All right. Good morning, everybody. I hope I'm audible. So let's begin with our lecture for the day. Okay. So let's continue with our analysis from yesterday. So yesterday we were looking at a simple circuit, which was basically an NMOS transistor, which is biased in saturation. Right? I pull the output from the drain. Right? This is my supply voltage, RD, which is the resistance connected to the drain. This is my MOS M1, right? And then I have connected a DC voltage VGS to this, right? And this VDS, right? And then I give a V in. So because of that V in, I will have a V out at the output. So remember, this is a DC voltage. And on top of the DC voltage, I given an AC signal, right? So let's first look at the DC condition. So now for the DC voltages, we know that M1 is in saturation. So this is something which you have to assume. So in reality, what you do is when you're designing the circuit for the MOSFET, you will design the circuit in such a way that you ensure that M1 is in saturation. So you make sure that you pick the bias conditions. You make sure you pick these voltages in such a way, you pick the resistance in such a way such that M1 is in saturation. So when M1 is in saturation, again, let's assume lambda is equal to 0. When M1 is in saturation, ID can be written as half Kn prime W by L VGS minus VT the whole square, right? Because lambda is equal to 0 in this case. So in this case, what you see is that ID is proportional only to VGS, right? VDS, it's immaterial. So if I want to calculate what the value of VDS is given by VDD minus, so VDD is the entire voltage drop from supply to ground, out of which some potential will drop across the RD resistor because this current ID is flowing through RD. And so this is given by ID RD, right? And so therefore, if I want to connect VDS, ID and VGS, VDS can be written as VDD minus half Kn prime W by L times RD times VGS minus VT the whole square, right? So this is how we connect these three DC parameters together, VGS, VDS, and ID, right? And so when you pick a VGS, when I say M1 is in saturation, basically these three values should be picked in such a way that this equation holds. Now what we said is, now let's assume we have now applying the AC signal on top of it, right? So therefore, your VGS can be now written as VGS plus some V in. And because of that, you're going to have the current, which is going to fluctuate around its DC point with some frequency and magnitude of ID, right? Now here, because we don't have any capacitive elements in our circuit, the frequency of all these signals is going to be remain the same. Second thing, remember, we are dealing only with linear systems, so there's no distortion. And when I say no distortion, essentially means that if I give a frequency, if I give a signal with a fixed frequency as the input, the output will have the same frequency as the output, right? So as the input. So we are not going to worry about change of frequencies. There are different circuits which can do that, but we learn that later in ADVD. So for now in this class, we'll say that if I'm giving a 60 hertz signal at the input, I will get a 60 hertz signal at the output. The current will have a frequency of 60 hertz. And similarly, because of this, your VDS is going to fluctuate by VDS plus or minus V naught, right? Now, remember that even because of this fluctuation in the signals, M1 has to remain in saturation. So we have to ensure that even when you added this AC signal, now the good part is this AC signal is going to be substantially smaller than the DC value, right? So this number, the magnitude of the AC signal, is going to be much smaller than whatever the DC value is, right? So, but in any case, when you're designing the amplifier, you want to ensure that M1 continues to remain in saturation for all acceptable voltages. So ensuring M1 remains in saturation, this equation 1 continues to hold. So equation 1 continues to hold. So therefore now I can write my equation 2 as VDS plus V0 is given by VDD minus half W by L into Kn prime into RD into VGS plus Vn minus Vt the whole square. Right? So equation 1 and 2 hold at all times because the transistor is always in saturation. Now we want to find a relationship. So what is the gain? Now if I want to find the gain of this circuit, the gain or the small signal voltage gain of this circuit is nothing but V0 by Vin, right? So I want to calculate this gain A of the amplifier. I want to know if my input signal is 10 millivolts, what does my output fluctuation look like, right? So what I'll do, so I want to find relationship between V0 and Vin. So I need to eliminate all other terms from the circuit. So let's subtract 2 from 1. So if I subtract 2 from 1, what do I get? I get V0 is equal to VDD get cancelled. I get minus half Kn prime W by L RD, right? This term, so I've pulled the minus out. So this term is VGS plus Vn minus Vt the whole squared minus this term, which is VGS minus Vt the whole square, right? Now, so let's expand the thing within the brackets. So if I expand within the brackets, I get V0 is equal to minus half Kn prime W by L RD. Right? Let's club these two together. So it becomes Vg minus Vt the whole squared. So I can write this as Vg minus Vt the whole squared, right? Plus 2 times Vin VGS minus Vt plus Vn squared, right? Minus VGS minus Vt the whole squared, right? I'm just expanding what is within the bracket. This cancels, right? And now what we're left with is these two terms. Now again, what we're doing is a linearizing term, right? So this, like, so now we know Vin is much smaller than VGS minus Vt, right? Because that is the definition of the amplifier, that our input signal, this is small signal because we are assuming small signal, right? Small signal definition means that your input output signals are all going to be smaller compared to the bias voltages that you have, right? And so when we have a condition like this, I can ignore the square term with respect to the linear term, right? Because Vn squared therefore implies that Vn squared I'm going to approximate to 0. So if I neglect this term with respect to the rest of the terms, I get V0 is minus half Kn prime W by L RD into 2 times Vin VGS minus Vt, right? 2 and 2 cancel. So what I'm left with is minus Kn prime W by L VGS minus Vt into RD. Suppose I bring the Vin back here. So V0 by Vin, which is nothing but the gain of the amplifier, is given by this. Now what is this term? Kn prime times W by L times Vg minus Vt. Do you know if it's related to some of the transistor small signal parameter? Anybody?
T overdrive.
No. What is this term? Kn times. So What is the value of transconductance? Gm is equal to what? Gm is nothing but dou ID by dou VGS, right? In saturation, which is Kn prime W by L VGS minus VT, right? And so therefore what you get the gain as V0 by Vn, which is given by minus GMRT. So let's let's look at this equation a little bit carefully and let's try and understand what is happening in the circuit. So first and foremost, let's understand what is the meaning of the negative sign. So does everyone want to think about what that negative sign means? Going back to the circuit. What
You're
does
180-degree out of phase.
180? So which means that when Vn increases, so how do we make sense of it, right? So when Vn increases, right? Suppose I've biased it at some 1 volt or 2 volt or something. So when the gate voltage increases, the M1 is going to pull more current, right? The saturation current in the transistor is going to increase. When the current in the saturation transistor increases, more voltage is going to drop across the RD resistor, right? And therefore, this voltage VDS is actually going to drop. So when the voltage at the gate increases, the drain to source voltage drops, right? And so therefore, what you're seeing essentially is that when V in is positive, V out is going to be negative in this transistor, in the way we have connected this transistor. And that is because of the fact that your current, when you increase your gate voltage, your current increases. Because of that, the drop in the RD increases, and hence this voltage is going to go down, right? And so that is the first thing you see, is that this negative sign means that V0, or the voltage at the reduces when gate voltage increases. Or in other words, if you just look at the small signal part of it, as Tanay just said, the small signal V0 is out of phase with respect to V1, Vin, right? The second thing you notice is that the gain depends on the transconductance of the amplifier, of the transistor, right? So if I want to increase the gain, I need to increase the transconductance. So the DC values of the circuit set the transconductance, right? So this transconductance values is set by your circuit design, right? And so based on that, hence your gain depends on where you bias the circuit. So therefore, this GM is proportional to VG minus VT, right? So if I increase VG minus VT, what happens? If I increase VG minus VT, I will increase the voltage gain of the circuit, right? So this is how we will play with the gain. Though again, remember, whenever you do design of amplifiers, when you're doing design of analog circuits, you have to worry about two things. When you have to design for a particular gain, right? The gain depends on the DC biasing of the circuit. Hence, biasing of the circuit will be something which will be very important, and we'll spend a lot of time understanding different biasing techniques, figuring out which is a better biasing technique, right? And looking at the ways as to how to quantify biasing techniques. How do we ensure that we are biasing the circuit correctly so that this gain remains stable? Because any small fluctuation in the biasing is going to change the value of GM, and it's hence going to change the gain, right? So we want a technique which are biasing the circuit in such a way that that biasing stays constant as far as possible, which means that our gain will reduce the variation in the gain. Because eventually when you're designing the circuit, you're designing circuit for a particular gain, for a particular predictive gain, right? And so when you're saying something is predictive, you want to ensure that you have full control on how that is designed. Now, obviously, what we've done in this right now through this whole process, we can, this is the ab initio method of doing it. Life becomes, it's easy to do in the simple one transistor circuit. And when we add multiple transistors, this thing becomes harder. So hence what we do is we do what is known as a small signal analysis of circuits, right? So what we do is known as small. So let's repeat the same with what is known as a small
There's
signal
a doubt in the previous
analysis.
slide.
Yeah,
So, I mean, VGS and VT can be very comparable as well, right? I mean,
VGS and VT. So we'll talk about. You don't want to be there. Yes, it will be comparable, but ideally you want your VGS minus VT to be a substantially high number.
oh yeah, that so that it lies in the saturation zone.
Correct. If
It
if your
reacts to,
VGS minus VT is the same order of Vn, then the transistor will not be in saturation at all times, right?
oh right, so that's why I mean
Right. Right.
small signal, and because we want it to be in the saturation,
Correct.
that's why it is very very hot.
Correct. Correct. So we can, you can, I'll, if I get to there, it'll be a nice assignment for you guys to go back and try and think about where you want to buy. So let me see if I can start the next chapter. We can, I'll give you a thought experiment to do for the at home. All right. So let's, so as I said, doing this analysis at all times is very painful. So we have to do what is known as a small signal analysis of the circuit. So so small signal analysis of a circuit. And what does that mean essentially is, so remember, if you look at RLC components, the RLC components, that is resistor, inductor, or capacitor, we know that they are governed, you can connect the current and voltage through linear differential equations, right? So V is equal to L di by dt, I is equal to C dV by dt, and V is equal to IR, right? So if you look at the three components, right, L di by dt is equal to VL, right? C dV by dt is equal to IC, and VR is equal to IR, right? So ideally, if you look at the three components that you have normally in all circuits, they are governed by linear differential equations, right? Which is easy to solve. Now, a transistor is a nonlinear element, right? Because if you look at our transistor model, it is not a linear. It has a quadratic expression, right? ID compared to VG. And so what we are essentially doing, as I told you, is we're taking these, when you do small signal analysis, we are picking a bias point and we're linearizing the circuit with respect. So that's exactly what we're going to do when we start analyzing circuits and when we do small signal analysis of circuits. So again, remember what a small signal analysis circuit is. We're looking at circuit behavior around the bias point. Right? And therefore, there what we're doing is once we pick the bias point, so the parameters of the transistor depend on where you pick the bias point. So once the small signal parameters of the transistor are known, then we go in and look at the small signal analysis of the circuit. Right? And the way, so this is something which we'll do it day in and day out in this class. So you have to be very comfortable with this small signal analysis of circuits. So how do we go about doing that? So the algorithm or the way we go about doing it is, let me just give you how to go about doing it, and then we look at the previous example and do it again. Okay. So one thing before we go forward, let's look at the circuit a little bit. I just want to highlight a couple of points. What can you say about the voltage at this point at the other end of the RD? Does that change when I apply a when I apply when I apply an AC signal to the gate? When I apply an AC signal at the gate, does this voltage change?
No, sir.
No, right? So remember, the voltage at the supply does not change. There is no AC signal there. Similarly, what can you say about the voltage at the ground?
It's also
Doesn't
constant at
It's
zero.
also constant, right? So these two voltages are not changing because of the AC analysis. What changes from both these is the current flowing. So the current, so what essentially means is this node, if you look at the AC analysis, this node, the voltage does not change, the current changes because of AC. So this looks like an AC ground. Okay? So that's an important concept that we'll do when we do small signal analysis. So the way we do small signal analysis, first thing is replace all transistors with their small signal model. Right? So we know what the small signal model of a transistor is in saturation. So again, here we will concern ourselves mostly with transistors in saturation. So we will assume the transistors in saturation and we'll replace the transistor with its small signal model. And second thing we'll do is all ideal DC sources, these ideal DC voltage sources are short circuited. And why is that? So as we looked at before, right? When we look at the supply, because of the fact that you've kept that node at a DC voltage, there is no fluctuation because of the AC signal. So that node essentially looks like a ground when you're doing AC small signal analysis. Similarly, ideal current sources, ideal DC current sources are open circuited. Again, this is very similar. We're just applying the boundary conditions because of the ideal DC source or ideal current source, right? And so now let's go back and look at the circuit. So now let's analyze this circuit using the small signal analysis. So again, for small signal analysis, I'm applying a small signal and I want to know what the small signal output is of the circuit, right? So remember, this is the gate, this is the source, this is the drain of the transistor. So always when you begin with this kind of analysis, first thing you have to do is identify the three terminals of the transistor, because eventually we are going to replace that with the small signal model of the transistor, right? So first you need to identify where the gate is, where the source is, where the drain is. Once you're done that, now we replace this M1 with its small signal model, right? Again, here we have assumed lambda is equal to 0. So let's replace M1 with its small signal model. So this is my gate node. This is my source node. This is my input voltage. So my input voltage here is V in, right? I've applied V in here. The small signal model looks like this. This is VGS, which means that if this is my drain, the current flowing between drain and source is GM times VGS, right? So this is my drain terminal, gate terminal, and this is my source terminal. Now, what do I see in this circuit? My gate terminal is connected to VN. So VN is applied between gate and ground. My source is grounded, right? Now let's look at the drain terminal. The drain terminal is connected to RD. So let's connect drain to RD, right? And then I have RD connected to a DC voltage source. So a DC voltage source gets short circuited. So this is my ground, right? And where is the voltage V0? V0 is drawn across RD, right? So this is my Vn. So V0 is drawn at the drain node, right? So this is my V0. This is my V. So this is the small signal model of the circuit, what we have done here, right? So we replaced the M1 with its small signal model and then ensured that all the DC voltage sources are short circuited and current sources are open circuited. When we've done that, what we've essentially created is the small signal model of the circuit. And so now with this, we can do a small signal analysis, right? So now here, what we want to find is, again, remember, small signal analysis is done to calculate small signal parameters, things like input resistance, things like gain. So in this case, we want to calculate the gain, voltage gain, which is nothing but V0 by V in, right? So how do we calculate the voltage gain in this circuit? So how do I calculate V0? V0 is nothing but given by the current flowing in RD, right? So if I look at the current flowing in RD, the current flowing in RD is GM times VGS, right? Now, because V0 is connected, so if the current is flowing from ground to V0 means V0 is a negative quantity, right? So V0 can be written as, if this current flowing through this RD is I, can be written as minus I times RD, right? Now we know from KCL that this I, the same, because V0, there's no other resistance connected to V0, whatever is the current flowing through RD, the same current is flowing through this branch of the circuit to ground, right? If I apply KVL into the circuit or KCL into the circuit. So which means that I have I is nothing but GM times VGS, right? And now, therefore, my V0 is given by minus GM RD VGS. Now, good part with the circuit is if you look at VGS, right? What is VGS equal to? If I want to connect VN and VGS, what is VN and how are VN and VGS connected?
VN equal to
Equal.
VGS.
VN equal to VGS, right? If I apply the KVL in this loop. And so therefore what I get is V0 is minus GMRD Vin, or the gain of the circuit is given by minus GMRD. So this makes life very easy, especially when we start doing large circuits, right? So it's you have to be very comfortable with this kind of process where you have to just replace transistors with a small signal model and then calculate the gain.
Sir, I just don't understand one part. What, like the supply voltage is just not in the diagram though.
Does the supply voltage impact the gain of the circuit?
Um, it depends. Gain, no, sir, but the power.
No, gain. I'm not asking anything else. Does it depend? We are doing only this analysis done only for the gain. For power, etc., we have to go and do the full-blown analysis.
Okay, sir.
Right. So let me give you another related problem. Let's assume that
Excuse me, sir. Sir,
Yeah.
in the previous only the VD was short, grounded only, right? After the
VDD
RD.
is grounded, right? So therefore, this RD, there would have been a VDD here. Instead, I've just grounded it
Yeah.
here.
Okay.
Right.
Right.
So let's do an example. Let's repeat so repeat the previous example. Repeat the previous circuit and calculate the gain. Calculate the small signal voltage gain. When lambda is not equal to 0. So when lambda is not equal to 0, that is if I have channel length modulation, what happens to the small signal model? What is the difference between that? So let's draw the circuit and tell me what is the difference in the small signal model when I have a lambda.
We'll have an R naught in parallel to the GM.
Very good, right? So how would you do this? Again, first thing first is look at where the drain, gate, and source nodes are. So again, if nothing is given, also remember we're doing small signal analysis. So M1 is in saturation.
Sir, can you go to this previous slide for a while? Thank you, sir.
So M1 is in saturation. So let's first identify the three terminals: drain, source, and gate. Right. So let's draw the small signal model of M1 first. Now lambda is not equal to 0. So again, this is your gate, source, drain. This is VGS. Right. The model says that because of VGS applied, I'm going to have a current flowing between drain and source, which is GM times VGS. Because lambda is not equal to 0, I'm going to have a resistor R0 that is going to be present between drain and source. Right. So this is the small signal model of M1 when lambda is not equal to 0. Right. Now let's connect the rest of the nodes. So the gate is connected to Vin, right? Source is connected to ground, so Vin to ground here, right? And now if you look at the drain is connected to RD. This is your V0 again, and RD is grounded, right? So now you have to calculate the value of V0, right? So how do you go about doing this? What is the net current flowing in? So let's look at this. So how do you calculate V0? So if you look at GMVGS is the current flowing in this part of the circuit, right? So I need to calculate what is the current flowing in RD. So the good part is RD and R0 are connected in parallel, right? So if I want to calculate V naught, what is the net current flowing through the parallel combination of G naught and R naught and RD?
GMVGS.
Right. So if I want to calculate V naught is given nothing but minus GM VGS times R naught parallel RD. Right? Because the net resistance, and if I look at this loop, right? If I look at the KVL in this loop, GM-VGS is the net current flowing in the parallel combination of R0 and RD, right? Because R0 and RD are both connected in parallel. Now, how do you know they're connected in parallel? Because R0 is connected between node D and ground. RD is also connected between node D and ground, right? So even though in this circuit, you don't see that, when you do the small signal analysis, because of the fact that the source is also at ground and because VDD also goes to ground, right? This essentially looks like RD and R naught are in parallel with each other. So therefore, your V naught can be just written as, again, minus because the current is flowing from ground into V naught, GM VGS R naught parallel RD, right? And so therefore, and we know that VGS is equal to VI in. So therefore, your gain is given by minus V naught by V in, V naught by V in, which is minus GM R naught parallel RD. Right? So if I have lambda, then in that case, my gain is going to be GM R naught parallel RD. Now, is this gain going to be less than or equal to the previous case? Less than, equal to, or greater than the previous case?
Less than,
Less than.
Why?
because R0 is also in parallel now.
And so parallel combination of resistors, the effective resistance is going to be less than the resistance by itself, right? So when you have a transistor with lambda, then you see that the gain of the circuit is gone down. And again, remember, your ideal transistor, you want lambda to be high. So we when we build transistors, ideally we want lambda to be 0. That is, we want that transistor to look like an ideal current source in its model, right? When we do that, the gain is going to be high. So when you look at real transistors, lambda is never 0 in a real transistor, and it can go as high as 0.1 or 0.2 in real transistors. So you see that because of that non-ideality in the MOSFET, your gain of your circuit is actually going down. So when we do ideal analysis, when we have everything hunky-dory, when we think of great ideal transistors, right, it's fine, but expect that in reality, the circuit performance is going to be worse compared to what you assume when the transistor is real.
Excuse me, sir.
Yeah.
Sir, why is there a negative sign for V naught?
So current is flowing from ground into V naught, right? So V naught should be a negative voltage.
Oh, okay. Thank you.
So recall all your circuit analysis. That is, I'm assuming you guys are all comfortable with that. If not, go back and practice some of your questions in ES. Okay. So with that, let's actually now get to the fun part, and let's start with the first actual circuit analysis. So we'll start with the first part, which is known as, let's look at the different CMOS amplifiers. So we're going to look at various configurations of CMOS amplifiers. And these are the basic building blocks. So we'll see that real amplifiers, because of a lot of parameters that you need to design for, we build it with, we make a real amplifier with multiple building blocks. So the blocks that I'm going to teach you now in the first chapter are basically the building blocks for designing filters, amplifiers, arithmetic circuits, whatever you have, right? So let's talk about, we're going to talk about 3 kinds of configurations to use a transistor as an amplifier. First one is known as a common source amplifier. The second one is known as or short circuited as CS, common gate amplifier, which is CG, and a common drain amplifier, which is CD. This is sometimes known as the source follower. So we look at each of these in much detail. We'll try and look at, so the key skill that you have to learn in this is again, when you're solving large circuits, when you're designing large circuits, understanding these small components will help you design the larger amplifier. So you need to figure out, one, you need to learn how to identify if it is a common source, common gate, or common drain. What are the advantages, disadvantages of each mode of amplifier, right? And in the ideal world, I would like you to get into that. So by mid-sem time, you should be able to do these analysis in your head, whatever we did the previous small signal analysis. Because of the fact that we're going to be dealing with large circuits as we go forward, this simple analysis should be something that you should be able to do it in your head, right? So you should start practicing so that you're able to get to that point. So before we begin, let's look at what are the key design parameters normally when you design an amplifier. So as I said, we're going to focus on amplifiers in this class. So if I ask you, what are the design parameters for an amplifier? What do you need to, if I want to pick an amplifier, right? What are the things I need to look at? So based on what you've known so far and what you might have picked up in the last few classes of this course, can you tell me what you consider are the various design parameters of an amplifier? What will you design for?
Ideal gain, R out and Rn.
Good. So the first thing we'll do is the small signal gain. Right? So why are you using the amplifier for small signal gain? Also, as you guys have learned in the first tutorial, impedances play a large part. So instead of saying R out and Rn, I'm going to call them as the input and output impedances. And the reason I'm not calling as resistors, because eventually we will worry about the capacitances too. Right? So input and output. So for an ideal voltage amplifier, I want my Rn to be high or low. For an ideal voltage amplifier, should my input resistance be high or should it be low?
High.
Good. Remember, it's a voltmeter. I'm sampling a voltage. Right? So I'm sampling a voltage. So I want to sample a voltage and give out. So my input resistance is going to be high. What about my output resistance of an ideal voltage amplifier?
Zero, ideally.
Zero. Good. Okay. All right. Anything else that comes to mind? Any other design parameters that you can think of?
So the range of saturation region.
Good. So what we call about is what we call an amplifier parlance as voltage swings. That is, we want to figure out that transistors remain in saturation. What is the largest swing you can get at any node? So voltage swing. Very good. What other thing can you think of? So let me give you some. Supply voltage. As I told you, sometimes you have the ability to pick a supply voltage. Many times this may not be a luxury, but if there is, you would use that as a design parameter. Other one is power dissipation, right? You don't want to, remember, which we looked at in some of the initial classes, right? You don't want this amplifier circuit to dissipate a lot of power. So which means that if you can avoid, you won't want to use resistors in your circuit because resistors consume a lot of power. You want to figure out how can I do these designs without using resistors. Other thing which we spoke about is linearity, right? That is, I want to ensure that my gain is a constant and independent of the input signal magnitude. It's independent of the frequency of the input, right? So linearity is something which we want. And the other thing which we will worry about is noise performance. And this we won't do in this class, but when you're doing a voltage amplification, for example, okay, the output, you don't want the output signal to noise ratio to become worse than the input signal to noise ratio. And so, and because the reason is when you're dealing with real circuits, when doing with circuits which are on the field, It's important because noise is something which we have to deal with every day. So understanding how the circuit can reject noise and only use signal is something which you have to design for. And the final thing, which is not that big a deal right now, is speed. So you don't want an amplifier to slow, to be a slow amplifier. You want ideally to be instantaneous. Whenever I give an input voltage, I should get an output voltage instantaneously. Again, these two things we won't really look at in this class, but advanced analog classes, we'll go into looking at how do you measure the speed of the circuit, how do you measure the noise rejection of a circuit, and how do we design for reduced noise rejection. Right.
Sir,
So
can you
could
show the previous slide once? Thank you, sir.
All right, so let's start with the first
Yeah. So
building
could you
block.
explain what you mean by linearity in this key design parameter?
I want my V0 by Vn to be a constant, right? Remember, we looked at this. We want the input output voltage to be a constant times the input voltage. I don't want this gain to be a function of the input signal. Right? So when I say V0 by Vn, I want this to be a scalar term A. It shouldn't have any other parameters in it. That's what I mean when I say linear.
Got it, sir. Thank you.
Yeah. So let's go back, and so we'll start with the common source amplifier. So what we looked at just now was the basic common source amplifier. Now, why is it called common source? So this circuit is known as the common source amplifier. Right? Why is it called a common source? Is because input is applied between gate and source. Right? So if you look at the input is applied between gate and source. Output is pulled across drain and source. Right? So this is your input and that is your output. So the source terminal in this configuration is common between both input and output. So the source terminal is common between input and output. And hence this configuration is known as a common source amplifier. This specific case is known as a resistive loaded common source amplifier. Right? So now we looked at the transfer characteristics of the circuit, right? So we know that if I plot the DC, if I look at V in versus V out, this is my VDD, this is VT, right? So my transfer characteristics look something like this, right? So my V out stays at VDD till my input goes to VT. After that, it goes into saturation, and eventually it goes into the linear region, right? And now you looked at, so if I'm going to plot the GM of this transistor, right? Let's look at the current flowing through the transistor. So suppose I plot V in, right? And I plot the current, a DC current, right? So let's look at the small signal model, let's look at the large signal model again. And let's see, I want to plot ID versus Vn. So instead of V out versus Vn, I want to plot ID versus Vn. So how will this graph look like? Can anybody start me off? How would ID versus Vn look like?
Sir, till Vn becomes Vt, IT would be still 0.
Would be 0.
And
Very
then
good.
it increases quadratically and then linearly.
It will increase quadratically, okay. And eventually it will linearize.
Linearize, yes.
Does it asymptotically come to some value? Can you think of what it should asymptotically reach? Any idea what the current should asymptotically reach? What happens when VDS becomes very, very small? So remember what is happening here. As you start VN, right? Your VN essentially initially it's in cutoff. When you start turning the knob on the input voltage, right? You start pushing the transistor into saturation. So as the transistor enters saturation, right? Your VGS keeps increasing, your VDS keeps decreasing, right? So eventually the transistor leaves saturation and enters the triode region where VDS is very small and VGS is very high. So in the asymptote, when VDS becomes very, very small, what is the current flowing through the circuit eventually?
So VDD by RD.
Very good. So what you see therefore is that the current is approaching the VDD by RD. It never reaches VDD by RD. Because if VDS becomes 0, what happens to a transistor? What happens to current flowing through a transistor? VDS is 0. In the linear region and the triode region, if VDS goes to 0, what happens to the current?
0.
The current goes to 0, right? Remember, current has a VDS term, right? If you look at the transistor in the triode operation, transistor in triode is given by half Kn prime W by L 2 times VGS minus VT times VDS minus VDS squared, right? So if VDS goes to 0, then the current is going to go to 0 in our model, right? So to ensure that current flows to the circuit, you need to have some voltage drop. So again, this is a very important concept that to ensure that current is flowing through the circuit, you have to always ensure that VDS is a positive quantity, which means therefore you see that even Vout never goes to 0, because if Vout cannot go to 0, because at that point then the transistor shuts off, so there's no current flowing through the circuit, right? And so what you see essentially is that ID versus VN, you see that the current rises and eventually asymptotically approaches VDD by RD, right? So now what are the so again, now let's go back and now think about the small signal application, right? So what we did here is the large signal model. Now if we go to the small signal application, what do I need to ensure? So for small signal gain, right? What is it that we want to essentially ensure that, so remember, this is cutoff, this is saturation, and this is linear, right? So so for maximum gain or for high gain, small signal gain, which region of operation do you want the transistor to be in?
Saturation.
Saturation, right? So you want it to be in this region, right? So how do we ensure that the transistor remains in saturation at all times?
So for the value we got VDD by RD, we just neglected the VDS, right? I
said it's asymptotically. So what's happening as you push the transistor more and more into the linear region, right? Remember, it is in saturation, then it goes into triode and linear, right? So as you keep increasing VGS, right, more and more current flows through RD, right? So most of the VDD is going to drop across RD. So VDS starts going very, very small. So all I'm saying is that the current asymptotically approaches VDD by RD. It will never reach VDD by RD because at that point VDS goes to 0, right? But it will be at, depending on the way, how far you push the transistor, how far you increase VGS, you keep increasing VGS higher and higher, eventually this VDS is going to keep dropping smaller and smaller, right? But asymptotically, the current is going to be VDD by RD, but it's never going to reach that point. It is going to be close to VDD by RD if your VGS is very, very high. Is that clear?
Yes, I got it.
Yeah. So what do we have? So to ensure that M1 remains in saturation, right? We want to basically ensure that VDS of M1 is greater than or equal to VGS minus VT, right? Or in other words, VDS is nothing but VDD minus IDRD should be greater than VGS minus VT, or IDRD should be less than VDD minus VGS minus VT. And this, as I told you, sometimes we write this as VOV, right? So this is an important term that we need to. So when you design that circuit, we want to ensure that we pick the values of RD, we pick the values of VGS in such a way that this equation is always maintained. Because otherwise, you're not going to ensure M1 is in saturation, which means that you're not going to ensure that you're getting the high gain. Now, also we did the small signal analysis. So from the small signal analysis,
Sorry, so what is VOV?
overdrive, VGS minus ET sometimes is written as VOV. It helps with remembering the formula because then I can write my ID as simply half Kn prime W by L VOV squared. So your textbook, so VOV is something which Sadra Smith uses quite a bit. So I just want you to get familiar that sometimes instead of VGS minus VT, we'll just talk about what is the overdrive. Right? Overdrive means what is the gate voltage above the threshold voltage. So from the small signal analysis, again, if I assume lambda is equal to 0, then what is the gain? My gain is given by minus GMRD, right? Or in other words, I can write this as minus 2 Kn prime W by L ID into RD. All I'm doing is substituting the formula for gain, right? So if I want a high gain, what should I have my ID or RD be? So if I want a very high gain from the circuit, what should should I pick a high RD or a low RD? What do you guys think? The voltage gain is proportional to RD, right? So if I want a high voltage gain, what should I do to RD? Should it be higher or lower?
Higher.
Higher, right? What about ID?
Yes, higher.
Higher, you want high GM, right? So you want ID to be high. What happens if you make a ID or RD higher? If you make them high, so if you make RD high, right? What happens? Basically, then even for small currents, this voltage becomes very large. So it becomes harder to keep M1 in saturation. So one of the big drawbacks with this kind of a circuit is that for high gain, right, you want high RD or you want high GM. But both of those are going to ensure that the transistor gets out of saturation early. So basically what's happening is you increase your RD, this range is going to shrink, right? So this is one of the drawbacks of this block is that if I just use a resistor and a transistor connected in series, and if I look at the gain, what is going to happen is, so for high gain, I want ID and RD to be high. But that implies that it's harder to keep M1 in saturation. So you see that there's a trade-off directly right here. So which means that you'll have to be very careful about picking the parameters. You can't just optimize it and say that, okay, just go with high RD and that's going to give you the highest gain. It's going to give the highest gain, but it's going to give you a very low voltage swing, right? There's no point getting a gain of 10,000 if your transistor gets out of saturation for any voltage higher than say 10 millivolts, right? So that is the trade-off that we have to continuously keep in mind when we're doing design. Okay, so we'll stop here. We'll continue with this in the next class. Okay, I'll take any questions that you might have.
Sir, in the small signal model, where we were considering the channel length modulation, if VDD is not grounded, then R0 and RD won't be parallel, no?
But VDD will be grounded in small signal. No? If that is the definition of that is the meaning of small signal analysis, right? So if you look at small signal,
grounded.
Let's go back to that slide. So if you look at, is my screen visible?
Yes, sir.
Yeah. So if you look at this right here, right, this voltage is never going to change when the node which is connected to VDD, right? So no matter what happens, this node for AC analysis is a ground because this voltage never changes. So so this node basically has to give a current, so it functions like a ground. So if you look, basically RD is going to be, now we look at this, we look later. Suppose I add a resistance in the source and source side of the MOSFET. Then in that case, what you're saying is true. When I connect a resistor here at the source, you'll see that no longer I can consider R0 parallel to RD. And then I'll have to find a different expression for the gain. So in this case, because of the fact that the source is also grounded and eventually RD also in small signal falls between this drain and ground, R0 and RD are in parallel. Now, when we start doing what is known as source degeneration, that is when we connect a resistor to the source, you'll see that this is not true. And then we'll have a different expression for the gain.
Sir, how does ID increase the gain of the amplifier?
So if you look at, if I just think about it purely from a point of view of GM, right?
Yes, sir.
If I increase ID, then basically my GM is also going to increase, right?
Yes, sir.
And so that's why. All I meant was, suppose you want to get a high gain. So one of our aims, so why do we want a high gain? We want a high gain just because if we can design for the highest gain, then any other things we can trade off that gain for that, right? So ideally we want that gain to be as high as possible. And so if I just take this very simple circuit, if I want a very high gain, I just basically need to pick RD to be very high or GM to be very high. Now the problem with both cases, so the way we do RD high is we can put a large resistor there. The way we do GM high is we push a large current through the transistor. So, or in other words, we apply very high VGS, right? That's one way to get large current. But in both cases, what you see is when you do both these, you're basically reducing the range over which the transistor remains in saturation, right? So therefore, if this range reduces, basically that means that you don't have a lot of wiggle room for your large gain, right? At no point do you want the total voltage at V0 or at Vn to be in such that this transistor gets out of saturation, because then our analysis goes wrong, right? So because of that, what you're seeing is that there is no optimization possible here. If you want high gain, you're going to live with very low swing here. So we'll see how do we fix this? How do we ensure that we get a better configuration? So we'll spend some time thinking about what is the load and how do we make this better? How do we improve? How do we increase our design window? See, all we are doing in this class, or whenever when we do circuit design, is we want to have large enough windows so that we can do optimization. I think at the last class somebody asked, right? So this is all a matter of running different optimizations, we're changing parameters and finding the space and doing an optimization, right? And if you have a optimizing function, then it's easy to do. All we're doing when we do design, so that is exactly what we do in design. The way we design the circuit is so that we ensure that we have large enough ranges on the various axes, so that when we design the surface, when we're doing the optimization surface, it's as large as possible so that we can find a good maxima or a good minima, right? So ideally, we want to design circuits which allow us to explore larger ranges for all the various components that we have in the circuit.
Yes, sir.
So could you move to the slide of CMOS amplifiers?
Sir, I have a doubt. Will you be uploading the tube slides?
Yes, I will. Sorry, I forgot about it. I will upload all of them.
Okay, sir. Thank you so much.
And sir, could you move to the first slide? Thank you, sir.
Yeah. Any other questions? If not, I'll see you tomorrow. Thank you.
Sir, I have a doubt. Sir, you mathematically showed that the output voltage has a 180-degree phase shift, but physically, what is actually happening in the MOSFET that we get?
That's what I'm saying, right? So suppose I increase the gate voltage. When I increase the gate voltage, the MOSFET is going to draw more current. When the MOSFET draws more current, more voltage falls across RD, right? Because the current flowing through the MOSFET is the current flowing through RD. So therefore, what happens? Therefore, this voltage, if you look at the voltage at node D, the voltage at node D actually is going to reduce if VGS increases. Is that clear?
No,
when
sir,
I increase the gate, sorry.
Sir, I'm asking why is there a 180-degree phase shift? That's what I'm asking.
No, the 180-degree phase shift, that's just the convention. What we're essentially seeing is that if I increase the gate voltage, my drain voltage is going down. That's all it means. Now this 180-degree shift and all, whether it's useful or not for us, that is something we need to think about later. But all that 180-degree shift is coming about because of the fact that if I increase the gate voltage, my drain voltage is going down. If you go to our output, if you go to this, right, this is what is happening. Now, if I increase V in, my V out is going down.
Yes, sir.
Right? So that is the same thing you're seeing, is that it's only in small signal is all you're doing is you're linearizing this around a point. But in reality, what you see is if I increase the gate voltage, my drain voltage is going down. That's all it means.
Oh, okay, sir. Got it.
Yeah.
Thank you.
Yeah. All right. Thank you.